Hey everyone, today we're going to be looking at some very basic natural language processing in Python, and our end goal is to create a basic text summarization program. So first, let's look at the logic behind creating our text summarization program. Essentially what we're going to be doing is we're going to break down the text we input into individual sentences, score each of the sentences on its importance, and then take our most important sentences and concatenate them back together to form our summarization text. For our basic program, this is an easy way to make sure our output text actually still makes sense. But if we started chopping up the sentences and taking the bits and pieces that we thought were important, we'd have a much more complicated problem to deal with. And today we're just going to be covering a pretty basic approach. And the way we're going to score our sentences to see which ones are the most important is we're going to look at all the non-punctuation and non-filler or stop words and see which ones come up the most. We'll then use the frequency of each of the words as a score and go through each sentence and score it by adding up all the scores of the individual words. So it's essentially like we're looking at each sentence and saying how many of the most common words do you contain, and that's how we're going to rank the sentences. And then we'll order the sentences by their kind of like importance score, and then we'll take the n most important ones and piece them back together for a summarized text. And n is just a parameter of how many sentences we would like it to condense down to, and we can pick n. And to help us do a lot of the splitting up into sentences and words and to filter out the stop words, etc., we'll be using some libraries. And so I'm going to set up, I've already set up a Python file in Visual Studio Code, and I'm going to go through all the libraries I'm going to make use of before I start coding. So here's the template I kind of have set out. Down here, so the reason I decided to have the text written as an input, like as a text file, was because, as you can see up here, commented out is just like a standard input statement where you can retrieve text. It was much easier just to copy paste a big article into a text file and then automatically remove the next line statements to make it easier to read, rather than pasting like a huge amount of text straight into the box. And every time we hit a new line, it would like exit, and it was just much easier to do it this way. But you're welcome to do whichever method you like. I've seen like web scraping approaches too, where the input comes from a certain website, so that's useful as well. And then once we've saved our input as a string, we'll print it out so we can take a look at it. It will ask us for how many sentences we want to narrow it down to, and then it will run this function right here with our text and n, and we're going to fill this in as I go through and explain to you guys what's going on. So let's begin with the imports. So first, we're going to import a couple of methods from the NLTK Python Natural Language Processing library. The first one we're going to do is we're going to import the two libraries that help us split a large amount of text into sentences and into words. So tokenize splits up whatever you give it into sentences. So it splits it by periods. And then word tokenize splits up literally everything. So it will split up by blank spaces, essentially. So when you run word tokenize on, say, a regular sentence, you'll get back an array of commas and words and things like that. And when you run send tokenize, you'll get back an array of the individual sentences. And we're going to use that when we're splitting up and scoring each of the words and the sentences. The second one we're going to be using is also from the NLTK library, and it comes from this right here. So the corpus is like a very large collection of words and things like that, and we're specifically interested in stop words. So stop words are things like the, and, or, so they're kind of like filler words. And later on, we'll see that we're only really interested in words that aren't stop words, right? Because like and the doesn't really, just because we found that the most common word in the article was and, doesn't really make the word and very important, right? Like we want to get rid of those words because they don't provide any context towards the greater article. And the last one is also along this line. It's punctuation. So we're going to want to filter out stop words and punctuation. Okay, sweet. Next, when we split everything up into words and then try to figure out how often each unique word occurs, we're going to use a frequency distribution. So it makes it really easy. We just give it a list of items, and it will return to us a list of all the unique items along with how often each of those occurs. So that's also provided to us by LTK and by the probability sublibrary frequency distribution, and that's what that will be used for. And then let me see the last one, the second to last. When we have, I guess I'll do it in this case first. Okay, so when we have our frequency distribution, it comes out as a dictionary, right? It comes out as a value pair. One value is the word, and the other value is how often it occurs. And so whenever we deal with that, we're dealing with dictionaries. And so we're also going to want to import a Python dictionary so that we can create and handle those as they come out. So dictionary. Okay. And then finally, when we want to sort our dictionaries, when we sort an array, we can just type sort and then parentheses the array we want to sort. But when we have dictionaries that have two values for each entry, it's much easier to use like a different structure, right? Because when you say sort something, it assumes there's only one value to sort by. Right? I don't think there might be a built-in functionality, but you kind of have to do a workaround. Versus if we import something that naturally supports specifying which of the 2 or 3 or however many values there are in a single entry to sort by, it makes it a lot easier for us. So we're going to be using a heap queue. Port and largest. So this will help us give it a dictionary mapping the sentence to its score, and then be able to sort those sentences by their score to see which ones are the most important to us. Something that would be kind of tricky to do if we were just using a standard sort function. Okay. I think that's about all the imports we need. Yeah, I think that's all of the imports we need. Okay, so let's start over here by summarize text. So the input for this function is the original text, so like the full text that we're trying to summarize, and how many sentences we want to summarize it down to. So first, we want to split the original text into an array of sentences so that we can have those and then later assign the like importance score to each of those. So sentences. So we use the send tokenize function, and we pass an original text, and then that will give us a list of all the sentences separated. And I guess we can put in like an error check here that if the length of the sentences is less than n, so if we say we want to summarize an article down to 2 sentences, but the article's only 2 or 1 sentences, then that makes no sense, right? So then I guess we can return error, article too small to summarize. Right, and they'll return this string back to print out rather than the summarized string. Okay, so let's take a look at what those sentences look like really quickly. Let's see, diff, sentence rankings, expected indent block. Okay. Okay. That's not expected indents right here. I think this is indented incorrectly. Let's see if that fixes the issue. Might be because there's nothing. It might just be because these are empty. Okay, cool. So what I put inside the text file as our example is an article on blockchain. So say we specify 3. I mean, this is irrelevant because we haven't done anything. So it says 54. Summarize text. Concatenating string. Not non-type. I guess it's running through here, returning none, and we can't have none. So we need to return something since we haven't filled that in. I guess we'll just do like null. Let's see if that works. There we go. Okay. So I mean, I just filled this in at the bottom so that we could actually get some output. So as you can see right here, this is what it looks like when we split by sentences. So it literally just takes the original sentences and it splits by the period right here, and then it goes into the next one. So now you're just left with an array of sentences. I guess that was probably pretty straightforward. Okay, next. The next step is we want to separately kind of get all of the words, the unique words, and see how often they occur, right? And the way we're going to do this is by first getting the words. So let's do that. We're going to use not sent tokenized, but word tokenized this time. Because we don't want the sentences, we want the individual words. Original text, and we want these all in lowercase so that we can compare apples to apples, right? We wouldn't want a frequency distribution for the word tree to show up as 2, and then another one be lowercase tree and that show up as 5. We would want a single lowercase tree with 7, right? We want all of them to be collected together because to us, in context, it doesn't really matter if it's lower or uppercase. It means the same word. And I don't think that's worth printing out. It's essentially the same thing as the sentences, just individual words. Okay, so third step will be we want to eliminate all of the words that don't mean anything to us. So we want to take away all of the words that are the and the filler words. We want to take out commas, periods, speech signs, things like that. Things that we're not really interested in. And so I already have a function up here that says get non-stop words. So we give it an array of words and it will return to us all the words that aren't stop words. So let's fill in that logic first. Non-stop words are going to be equal to get non-stop words. And so we pass these words up into our function. So now we just need to write the logic for this function. Okay, and this is where these libraries are going to come into play right here, because we're going to essentially say for each of these words, are they included in either of these libraries? If they are, we don't want them. And then whatever we're left with must be non-stop words, and we return that. So first we're going to compile a list of stop words, and this is kind of a little bit like you kind of have to just trust me on this, and you can search this up online. It's a pretty cookie cut a straight cut thing. So stop words, dot words, English. So this returns to us all of the English stop words contained within our array of stop words, right? So it kind of, let me see. So it looks at stop words, and it looks at our list right here, and it checks how many of these are included, and then we want to add punctuation as well. Hold up, did I say that correctly? I think I might have said that wrong. I think I just had the same variable up here. Let me see. Okay. Let's change this variable around. Change this to my words. Okay, that makes more sense, right? This words has nothing to do with that. So this is stop words, and then I guess a sub category of stop words. You just say words, pick English, add all the punctuation, and now what we have is a combination, a big list of ands, all the words we don't want, and all the punctuation we don't want. That's kind of all you need to know about that. And now we're gonna see what are the words that aren't stop words, essentially. So for my let's see, for my word in my words. So we're going to loop through all of the words that I just gave to this function, and we're going to see which one of these are stop words and which ones aren't. So if my word is not in stop words, so in other words, we want to keep it, then we add it to the output array. Okay. Okay, let me go through that logic one more time so it makes sense. Up here, we're making a collection of stop words from these two libraries, 1, 2, stop words and punctuation, and then we're going to start collecting and filtering out which one of our words we want to keep, right? Which one's important to us, we don't want the stop words, and then we return that. Okay, so let's take a look. Don't want to put this out anymore. Let's see what the non-stop words are. And also, let's see what all of the words are. Maybe actually not print this because that's kind of a lot to look at. Okay. So 4. If there is an error in line 66, reference get non-stop words. 41. Okay. Get non-stop words. Try this again. 4. Okay. Cool. So I guess I should split those up so I could see the difference. Function, get non-stop words. It's also a mistake. Okay, here we go. Alright, so you see this is a lot smaller than this list, and that's because this list, so you get blockchain. Right off the bat, we don't see that comma here. We don't even see which, because which is kind of like a filler word. It like connects a bunch of other words together and doesn't really add anything to what we want. Again, to isn't included, emerges, real word, as and a aren't included. So you can see like we're only left with the words that add context and really add importance to our article, essentially. Okay, so let's move on. So now our next step is going to be to create a frequency table to see which of these words occur how many times, and then we're going to use that to see what the most important sentences are based on that. Okay, so we already imported a frequency table library, so all we have to do is use that. So frequency distribution, we want to put in the non-stop words, and let's see what that looks like. Go. Okay, I guess it can't display it. I mean, I guess it's not too hard to imagine. It'll look, I mean, I know this works, so it'll look something like this. It will have the word, I don't know, blockchain, and then however many times it occurs, right? So we'll have that in a list. So I have a bunch of these together like this. And I have a different word, say it's tech, and this one occurred 10 times, right? So that's what we will get. And all of these will be unique, right? So if tech occurs 10 times, it'll gather up all the techs, add them up, put them in here one time, and that's kind of what that looks like. Down here, what we're seeing is just, it's referencing the frequency distribution object. Okay. So with that frequency distribution, we're going to use it, and we're kind of going to treat each word's frequency as its like score, as its importance score. So every time we see that specific word in a sentence, we're going to add that score to the sentence's score, and then add that up to see how important the sentence overall is. Like, how many important words does this sentence include? So, like I had before with the get non-stop words, I also have a function for this, you know, so it's a little bit easier to read. So we're just going to fill in the logic down here to call that function, and then we'll go about to fill that out because it's a little bit more difficult. Okay. Sentence scores. get sentence rankings, and we're going to pass sentences that we did right at the start. We got the sentences, and we're going to pass the frequency distribution of all the words, right? Okay. So when we go up here, so we have to keep in mind that the sentences is a 1D array. So it looks something like sentence 1, sentence 2, etc. And then the frequency distribution looks like what I just showed below, right? It was it's gone now, but it looks something like this. So it looks something like word, and then the score or the frequency, right? And it had a bunch of those. So what we kind of want at the end here to get sentence ranking, what we want is we want on one side we want the sentence index, and on the other side we want the sentence score, right? So that now we can see, we can rank by the scores and see which are the most important sentences, right? So how do we achieve that? We're going to use a dictionary, because a dictionary lets us set up those like two variables, right? It lets us create a list of things that have two values. And so we'll start off. That's also why we imported. That's also why we set up. We imported the dictionary up here so we can use it down here. So sentence scores, default dictionary, and okay. So we're going to loop over all of the sentences that we inserted here and calculate the score for each one. Sentence in sentences. So what this statement right here does is it says for, it's essentially a for loop. So enumerate literally means get how many items there are in sentences. Say we have 5 sentences, so loop 5 times, and for each one it will get the sentence or the item at that index, and it will also provide us a value, like a number to reference by. We're going to need to use this later. That's why usually you could just have for sentence in sentences, but for our purpose we also want to keep track of the index, because we're trying to assign index to value. Okay, so for each of these sentences we are going to check what the score is. So in order to do that, we need to grab all of the words inside each sentence. So this will look similar to what we did before. So right here, what this does is it sets up another loop. So this is for each sentence. This is for each word in the sentence. And this will look familiar. We get the sentence, we get the lowercase sentence. We split it up into each of its words, and then we iterate over each word. And for each word, we want to check if it's in the frequency distribution, and if it is, what its score is. So, and the reason we say if is because this right here will probably also give us commas and filler words, which won't be in our frequency distribution. And so we don't care about those. So if the word is in the frequency distribution, which we passed up here, then we want to add its score to the overall sentence score. Sentence scores. Okay. So if the word is in our frequency table, which means it's important to us, then we want to add its score. And the way we do that is we go to the frequency table, we check how often this word happened, and we add that to the sentence's score. And this is where I comes in, because we're ordering, we're going to save these by the index of the sentence. And you'll see this comes in play later, because we're going to want a way to arrange the sentences back to their original order. So once we're done figuring out which are the most important sentences and all that stuff, and then chopping it off at maybe we wanted to summarize it down to 3 sentences, now we need a way to figure out, okay, with these 3 sentences that we have left now, what order do they go back in, right? What was their original order? Even if there's other sentences in between that we've chopped out since, what order do we need to put these in to make sense, so that it logically makes sense in reference to the article. So that's why we need to keep track of that. So once we've gotten all the scores for all the sentences, we just return. Okay. Okay, so let's take a look at what that looks like. So this right here, okay, that should be fine. Let me see. Yeah, let's see what that looks like. See if the dictionary actually gives us anything useful that we can see, and it might just give us like a dictionary object. Oh, okay, cool. All right, so as you can see right here, we iterated by I so that we would maintain each of the sentences kind of order. So you see the first sentence had a score of 27, second one had a score of 47, third one had a score of 45, and we keep going. So I mean, that already tells us there are 12 sentences, and the words within these sentences must have added to this score. And the way we got to that score was by taking the frequency distribution and kind of just adding together how often each of these words happened overall in the text. So that's looking good. So the next step is we want to sort this, right? So we have a dictionary now. We want to get this which one would be the highest? 49. Where this is right at the front, right? So sentence 6 has the highest priority and the highest importance. So we want to find a way to sort this. And since every single entry has 2 values, we need a library that's going to allow us to sort by this value. And because like if we just said sort, the method, the function be like, well, which one? We have 2 values that we could be sorting by. So that's why we imported this this heap right here. So let's go ahead and do that. So n most important, just sentence indexes. N largest, we pass in n, because I mean you could say 5 or whatever, but we already gave n, right? Just happens to be the same variable. We said we only want the n most important ones, so n, and then we do sentence scores. But then we also want to specify how we want these sorted, right? So we want these sorted by the sentence scores, which, as you can see down here, would be the second variable. So it's going to go through and sort by all these entries' second value and return to us. See what that looks like. most important sentences, indexes. It's giving us a blank. See, maybe n largest. Why wouldn't? I mean, I guess it is an n largest object, so it might just not be able to display. Oh no, actually, why am I saying that? Okay, it says it right here. Okay, yeah, cool. All right. I don't know why I overlooked that. So it literally just gives to us now, based on all of this, right? Based on these scores, it gives us the n most important sentences, right? It gives us the indexes of the n most important sentences. And so it says right here that the 7th sentence is the most important. 7th, 52 is the highest score out of all these, so that's correct. 6, 49, yep, that's the second highest, and so on, right? If we entered, say, 6, then it would give us the 6 most important sentence indices. So now with these indices, right, this essentially tells us that when we go all the way back up here to where we had the individual sentences, there's the word still, wherever we had the sentences, all we have to do now is go back, find the 7th sentence, the 6th, the 1st, the 2nd, the 8th, the 10th, and the 8th, and concatenate those together. Now the only thing we kind of would want to do is to make sure that, you know, it relatively as good as it can makes sense, is that we do the 1st, the 2nd, the 6th, 7th, the 8th, the 10th, right? So that at least they're in logical order, right? We already said these are the 6 most important, so there's no point in putting the most important sentence at the top, because we're probably going to read through the whole summarized article anyways, right? So let's go ahead and put those in the correct order so that we can go fetch the sentences and concatenate them back together. And so for this one, we can actually just use the normal sorted method, because we only have one variable to sort by. Sorted, and then we paste in this. Okay, and then let's see. And you should see that it literally just returns the same thing that we had before, just sorted this time. There we go. So it's the same one as this, just in the correct order now. So now all we have to do is fetch the 1st, 2nd, 6th, 7th, 8th, 10th sentences, put them together, and that will give us our summarized text. So sorted, first, previous one, so summarized sentences, an empty string, and for index in sorted most, I'm sorry that I used such long variable names. It just helps me keep kind of track of what I'm doing, but I think conventionally you should use something that's specific, unique, and tells you what the variable means, but definitely shouldn't be this long, because that's not efficient either. Sentences plus equals. Okay. Oh, what did I do there? Did I just close? Not sure what I just did there. Okay, we're back. Okay, so we're going to go through sorted most important indices. So we're just looking at these indices, each individual indice, and we're going to use these to retrieve our sentences, the ones that we split up right at the beginning, and we're going to use those split up sentences and put them back together. So that's what that plus equals does, and we add a space in between each, and we're essentially done. Summarize sentences, and let's see what that outputs. So show you what the original text looked like. Print the original text, and then print the summarized text. Let's say 5. 5 should be reasonable. I think the original one we said had 12. And so it's a big article about blockchain, and then down it gives us the 5 most important sentences, and it concatenates them together. As far as I'm concerned, as far as I've tested, it's pretty good. It's obviously it will miss out small details that are mentioned once and once only, but as far as general topics in the text, it actually picks it up really well, because if there's a general trend in a text, chances are that buzzwords will be repeated very often, and the chance is that those buzzwords will be at the top of the frequency distribution. And so when we calculate the scores of the sentences, the scores containing those buzzwords will have really high scores and will likely end up down here in our summarized text at the end. So, I mean, obviously, the more N is, the more accurate the results. But for something more complex where you want information to be extracted from each sentence and then pieced together using correct grammar, you definitely need to use a different approach, I'd say. For a simple example, though, this does the job, and you can also use individual parts from this project, for example, just the word frequencies. So you could do something on Twitter data, and you could graph, the most used non-stop or punctuation words. That could be interesting, and maybe you could build up your own dictionary of buzzwords for stocks. I don't know, stocks that you're currently trading, and every time those buzzwords are near the top of the frequency distribution after being, further towards the bottom, then you could buy with, the anticipation that the price will rise and that you can then sell it afterwards to make a profit or something like that. So there's a lot you can do, and some of the tools in this workshop can give you some pretty awesome results. Yeah, I mean, Python as it is geared towards this kind of stuff, but these libraries kind of make it even easier and put some of the more clunky things like, say, sorting, a dictionary into a black box model where you just put an input and you get an output, and it's quite easy. So yeah, I hope you enjoyed this workshop. I hope it's relatively easy to follow along, and that you learn some basic skills that you can apply to your next natural language processing project. And I wish you all the best. Thank you for joining.